Hello, I'm Jan Keim from the KIT in Karlsruhe, Germany, and I want to present our findings from our research where we looked into Bert's capabilities to understand code based on the use case of detecting architectural tactics in code. Bert is a statistical language model that tries to capture words, their relations to each other, and their semantics. Bert has proven to be really good in different natural language processing tasks and had state-of-the-art results in tasks like text classification on release. A central benefit of Bert is its transfer learning. You can train Bert on a certain task and then just need to fine-tune it for another specific task. The benefit of this is that you need much less data for fine-tuning because certain aspects are already learned beforehand. For example, Ruder showed that their approach outperformed other state-of-the-art approaches that were trained on 100 times the data. Additionally, there are pre-trained models of Bert available. This makes it easy to use the models and fine-tune them for specific tasks and test them out without the burden to train the whole model yourself, which is quite an effort itself. With Bert in mind, we looked at the problem of detecting architectural tactics in code. This task is a special case of design pattern recognition, but is more challenging, because tactics are described in terms of roles and interactions. Therefore, structural analysis only yield limited results. Approaches usually use the premise that programmers use meaningful terms, for example similar methods or variable names, similar wording overall, or maybe even similar comments. The current state of the art achieves an average F1 score in this task of 92% in cross-validation and 80% when applied to a case study. Here we asked ourselves, can we use language models like Bert and the transfer learning capabilities to classify code for the detection of architectural tactics? Additionally, we were wondering, do the available pre-trained models of Bert already understand code? With that, we first want to look more closely into Bert to get a rough idea how Bert can be applied for text classification before I present our approach. The pre-trained model of Bert is trained on a big dataset containing text from Wikipedia and Google Books. The input text first needs to be tokenized, where also additional tokens like the pooling token CLS or padding tokens are added to fit the input to a common length. These tokens can then be used as input to Bert. Bert processes them and outputs various vectors, where the first vector is the pooled output. This is a contextualized vector representation of the whole input. We use this as an input for our classifier layer, which is a simple single-layer feed-forward neural network. The output of this classifier layer is then the corresponding classification of this multi-class classification. In our case, we need to use code as input. However, we cannot simply use it as is, because there are a lot of special characters and unknown words that cannot be processed properly. Therefore, we pre-process the code, for example by separating compound words written in camel case or similar, and truncating classes so they fit into Bert with its maximum input size of 512 tokens. The rest stays the same like in usual fine-tuning for text classification for multi-class classification. The classes are here the architectural tactics that we want to find. During training, we fine-tune the classifier using a dataset of classes implementing architectural tactics as well as unrelated classes. We evaluated this approach first with a tenfold cross-validation. We used the same dataset as the state-of-the-art approach by Mirakhorli for comparability. In this dataset, we have the tactics audit trail, authentication, heartbeat, resource pooling, and scheduling. Additionally, we have the unrelated class that is used for classes that do not implement any tactic. In this table, you can see the results in comparison to different other approaches. For the sake of brevity, The results here are the average results over the tactics. More details and additional approaches for comparison can be found in the paper. The upper three approaches are among the best approaches that are implemented and evaluated in the paper by Mirakhorli and colleagues. Our approach here achieves good results with an average F1 score of 90%. This is comparable to the other approaches. The differences between the approaches are here not statistically significant. Next, we evaluated the approach on a case study. We used Hadoop as our case study for this. Again, we used the same dataset with the same architectural tactics provided by Mirakhorli for comparability. We trained the classifier on the previous dataset of the cross-validation and then applied the trained classifier on Hadoop. The results here are again the average results over the tactics. The results are over the board worse than the results in the tenfold cross-validation. The results for all approaches are way lower than before. The numbers in red show the absolute change in percentage points. For example, the Bayesian approach drops by 71 percentage points in the F1 score. Our approach also drops down to 53%. Only the tactic detection approach drops just slightly down by 9% to an F1 score of 0.8. Our approach here performs better than the other approaches except the tactic detection approach that simply outperforms our approach in this evaluation. What is also worth to note is that the results for our approach are pretty stable over the different classes, so we don't have any class that is much better than the other, whereas other approaches vary a lot. With these results, we want to briefly discuss these. Obvious questions arise around our research design. Questions like, is our design sound and is the dataset suitable? We think we can affirm these questions, and we also answer these more in depth in the paper. Further questions arise regarding our approach, which we all want, and we also want to tackle these in future work. For example, we think we still have to improve our pre-processing, especially truncation, as we think we might lose valuable information there. It is also worth to keep in mind that code, although similar, is different from normal natural language text. Here we have ideas to use other language models, maybe even language models that are trained on code, or maybe also use additional pre-processing that transforms code into prose text. Moreover, there are newer language models that allow for longer inputs that we want to test here. Moreover, we were wondering if we can exploit transfer learning capabilities of these approaches or these language models even more. We want to benefit from the probability that less data is needed, but for this we probably need a more suitable language model that is more suitable for code. So to sum up, we had the idea to use Bert to classify code regarding architectural tactics and explored this idea. We had two major research questions. The first was if pre-trained models of Bert already understand code. We can say that Bert does to some extent seem to understand code, but a lot of the semantics might not be properly grasped. Regarding the second research questions, whether we can use Bert for the detection of architectural tactics, we can say that our results were promising in the tenfold cross-validation and on par with other approaches. However, the state-of-the-art approaches outperforms ours in the evaluation on the case study. This is all for now. Thank you for your attention and feel free to ask me any questions.